modeling wildland fire spread using Eulerian level set method and high resolution numerical weather prediction. Dr. Lautenberger is a fire protection engineer based in Berkeley, California. His research interests include structural and wildland fire modeling, materials flammability, and solid phase combustion. Chris has recently been working in conjunction with telecommunications companies, a major electrical utility, and the California Public Utilities Commission to develop a model that quantifies the associated fire ignited by overhead utilities. Chris is also an instructor of fire protection engineering at California Polytechnic State University, where he co-teaches courses in fire dynamics and fire modeling.
I would like to inform to the speaker that the time for presentation is 20 minutes. In order to control the time for presentation, a green card will be kept on the table, indicating that you are in time. When there are 2 minutes remaining, a yellow card will be placed on the table. The presence of red card means that the time has ended, so you should finish the presentation.
Well, thank you, Professor Lignon, for that introduction. And Marcos is certainly a tough presenter to follow, but I'll try my best to keep everybody awake. And looking through the program today, it seems that a lot of the presentations have to do with sort of fundamental fire modeling and applications to buildings or maybe industrial occupancies, as Marcos was talking about. And I'm going to kind of switch it up and talk about wildland fire modeling. And I've heard people say that fire dynamics in a wildland setting are much different than the fire dynamics inside of a building or a compartment, and that fire modeling in a building is very different from fire modeling for wildland fires. And certainly everybody's entitled to their own opinion, but I would certainly disagree with that characterization, because if you think about it, all of the physical processes and then their mathematical representations apply equally to a fire in a building, or a fire, say, on the International Space Station, or a fire in a wildland setting. So all the things we've heard about earlier today, soot formation and oxidation, flame radiation, things like that, all the conservation laws, thermodynamics, thermal radiation, all of that applies equally to a wildland setting. So I just wanted to maybe give a quick background on wildland fire modeling, or maybe one wildland fire model in particular, known as FARSIGHT, which is the Fire Area Simulator. This is a model that's been developed at the U.S. Department of Agriculture and Forest Service, and it's sort of become the de facto standard fire model in this area. And really the goal of fire modeling, or wildland fire modeling, is to be able to predict how quickly does a fire spread, how big does it get, and how long does it take. So in many ways, it's no different than what Marcos was talking about, where he's trying to predict how quickly does the fire grow and spread in between two parallel panels for a materials flammability test. Whereas here we just have different fuels. We have natural fuels, and there's some things to contend with, such as the spatial and temporally dynamic nature of the atmosphere that we don't have in compartment fires. But just to sort of reemphasize, all the controlling physics and science are more or less the same. But FARSIGHT really is a groundbreaking model in many ways. It does a really good job at striking a balance between, say, physical accuracy or complexity and ease of use. So FARSIGHT is widely used both by the USDA Forest Service as well as state governments and researchers. And although it's appropriate for maybe 95 or 99% of applications, there are some opportunities for improvement or maybe additions to this type of model. In particular, there's no option or no possibility of doing a Monte Carlo simulation in Farsight. You can run 1 or 2 or 5 or maybe 10 different simulations, but if you wanted to run, say, 100,000 simulations or 1 million simulations to look at a large geographical area, or maybe run different permutations of the same basic scenario where you're looking at sensitivity to inputs, there's really no convenient way to do that in Farsight. There's no DMP or distributed memory parallelization, so it can't be run on computer clusters. It's basically a Windows-based program, and the source code is not available, or at least there's no subversion repository that's under active maintenance and development. So at the heart of Farsight is something called Huygens principle, which was first proposed in 1678 to explain the propagation of light waves. And it's used by Farsight to propagate the fire forward in time as an ensemble of elliptical wavelets. So basically, if this is the fire perimeter at time t, each point on the perimeter is represented as an independent elliptical wavelet that moves forward in time and space proportional to the local conditions on the fire line. So at time t plus delta t, the fire perimeter might look something like that. And this actually works quite well for small fires and for relatively simple fires, but as the fire size increases and as the shape of the fire perimeter becomes more complex, you have to add a lot more points. It can become very computationally expensive, and it's also cumbersome when you have fires merging together, spot fires forming, because you have to have all types of specific logic for how you combine and merge these different fires. So really spot fire formation and fire mergers are a bit of a challenge with Huygens principle. So the objective of this work is not to really recreate the wheel, but maybe to just polish the wheel a little bit. Really to develop a wildland fire spread model in the same vein as Farsight that uses efficient modern numerical methods, and in particular leverages, say, message passing interface or modern parallel libraries that can facilitate batch mode calculations and allow you to run literally millions of simulations. And in particular, this would be done or is done using a Monte Carlo simulation to address spot fire formation, which is a stochastic process, as well as conduct sensitivity analysis and perhaps even some type of automated model calibration similar to what Marcos was talking about using inverse algorithms. And also, since this is being developed from scratch, it's an open source platform independent model. And hopefully in the long run that will facilitate testing of new physics routines. The model itself is based on a numerical method called the level set method, or LSM for short. And the level set method is a numerical technique for tracking interfaces. It's used in image processing, it's used in all kinds of things. And there's two flavors of the level set method. There's a Lagrangian approach, which is similar to Huygens principle, where you have individual points that are then tracked. And then there's the Eulerian method, which is where you track a curved surface on a Cartesian or a rectilinear grid. And this is the approach used here. And the Eulerian level set method is commonly used in simulations of premixed combustion, where you have a burned fuel-air mixture that's separated by a thin flame from the unburned fuel-air mixture. And what we're interested in is calculating the rate at which the flame propagates into the unburned fuel-air mixture. So it is been applied, and a lot of the numerics have been worked out in the area of premixed combustion. And really simulating a wildland fire with this approach is no different. Here we have the actual fire, where we have a burned region in the middle. This is the black area. We have the green area outside the perimeter. That's outside of the perimeter. That's the unburned area. And then the burned and unburned areas are separated by a thin interface that in a wildland fire we call it the fire line. And its representation inside the computer is shown here, where we have a fixed mesh, and we then have a curved surface that represents the location of the fire. And what we're interested in is calculating the rate at which each point along this perimeter propagates or moves forward in time and space. So the level set method really is a natural fit for wildland fire modeling, but it has been applied only infrequently in this area But there has been a sort of a pulse of interest in the last few years, starting in 2009. There's actually a level set method for wildland fire spread implemented by Riemann McDermott in WFDS, the Wildland Urban Interface Fire Dynamics Simulator. And also recently it was added to WRF Fire. WRF is Weather Research and Forecasting. It's a numerical weather prediction model that's been developed by the National Center for Atmospheric Research. There was also a paper presented this past summer in Warsaw at the Combustion Institute Symposium, where this was used for simulating wildland fires. And there's another one that's not shown here that I just learned about, where the PhD thesis was recently completed in this area using the level set method to simulate wildland fires. So it seems that it is gaining acceptance in this area, and I think really the reason for that is that it does offer several advantages over Huygens' principle, insofar as there's no special treatment required for spot fire formation, emerging fires, and things like that. As far as the mathematics of the level set method go, it involves solving this parabolic differential equation for a scalar variable phi. And there's different variations of this. In the premix combustion literature, this is usually solved for a variable c. There's a progress variable that varies from 0 to 1. Here we don't ascribe any physical significance to phi, other than for phi values less than 0, the state or the local state is burned. For phi equals 0, this is the level set corresponding to the interface between the burned and unburned regions. And then for phi greater than 0, we're in the unburned or the green area. All the physics here are lumped into these two parameters, ux and uy, which in the level set world is usually called the speed function. And in this particular context, it's the rate of spread. It's how quickly is the fire growing or spreading along its perimeter. And this has to be calculated in the direction normal to the phi field. So we figure out the normal vectors and then calculate the components of u, or the speed function, in the appropriate normal directions. And there's several possible ways that you can go and calculate this Vs, which is the spread rate. And the approach chosen here is to use the classical raw thermal method, which is sort of deeply entrenched in the Forest Service and a lot of the fire behavior calculations, at least in the US. And the raw thermal model relates the rate of spread to several factors, including factors for slope and for wind, fuel moisture content. All of that is buried into this equation here. But I should emphasize that the level set method is in no way married to the raw thermal model. It can be used for a different equation or a different approach that gives the fire spread rate as a function of the relevant variables. There are a few things you have to do to get this to work out right numerically. Riemann McDermott, when they implemented this into WFDS, proposed using a super B flux limiter. And I found that worked reasonably well, so that's used here. And they also proposed a second order Wimda-Kutta method, represented here, and that's used in this particular work to advance the solution forward in time. And so at the end of the day, you take this level set method, combine it with the raw thermal model, and run some simplified cases where you're looking at fire perimeters, and it turns out it's very similar to what is calculated with Farsight for these idealized scenarios, and that does make sense because Farsight also uses the raw thermal model. So I thought what would make sense to do is to just kind of talk qualitatively about some of the types of fire shapes and fire perimeters that can result from this model. And this was done for an area in Northern California, located just to the west of Lake Tahoe, in a fairly mountainous area, a fairly mountainous and remote area. And this was done as a forecast earlier in this year. There was a red flag warning that was predicted for this particular area in California. And we ran a Monte Carlo simulation to look at a few tens of thousands of fires in this area to get an idea of the range of fire sizes that could result under these red flag warnings, which basically corresponds to low humidity and high winds. This sort of angled red line here is the WRF domain that the wind and weather inputs were developed using high resolution numerical weather prediction with WRF, the weather research and forecasting model. And then this kind of yellow square is the fire modeling domain. So all the fire perimeters were modeled inside this area here. There's a lot of inputs that are required by this approach. And basically, as far as fuels and topography are concerned, we have things like elevation, slope, and aspect. Aspect is the direction that a slope faces. That's how the model knows sort of which way to pull the fire up the slope. There's other things related to fuels. There's the fuel model. This is a stylized representation of all the parameters that are needed by the raw thermal model to be able to calculate the spread rate. And then there's some things that are more important for developing wind reduction factors, which is the ratio of the wind speed at 20 feet to the wind speed at mid-flame height, which is what is needed by the model. And then there's some things related to crown fire behavior. So there's canopy cover, stand height, canopy base height, canopy bulk density. These data are developed by remote sensing, and they're available free for download from landfire.gov, at least for the US, at a resolution of 30 meters. So these are fairly high resolution data. And it's my understanding that similar data are also available internationally. So you can go to landfire.gov and download rasters or download layers for each one of these and then use them as input for the fire spread calculations. And just to give an idea what the data look like, here we have that wharf domain that I pointed out before. It's about 60 kilometers on edge. This is the Pacific crest here. So elevations here are something like 9,000, 9,500 feet, so 3,000 meters. And in these blue areas here, this is the American River Canyon, there are, the elevations are down to maybe 2,000 feet, 2,500 feet, so closer to 1,000 meters. So this is a fairly mountainous, rugged terrain, and we have similar layers for things like slope, aspect. This is the fuel model. This tells the type of fuel complex that is present as a function of space, and then other things, canopy base height, canopy bulk density, canopy cover, and so on. So that is sort of the easy part, because those things are stacked. Those aren't changing in time. What requires a little more effort to develop are the required wind and weather inputs. So we need to know, as a function of both space and time, the wind speed and direction, air temperature and relative humidity, and then these things feed into calculation of the dead fuel moisture content by size class. This is 1 hour, 10 hour, and 100-hour time lag fuels. It has to do with how large the diameter of the different fuels are. And there's many ways you can go about determining these wind and weather inputs. People often use, if they're looking at a past fire, input from weather stations, RAWS stations, remote automated weather stations. You can use, I would say, forecast from the National Weather Service. But in this particular case, we use numerical weather prediction using the WRF model, Weather Research and Forecasting, at very high resolution, which for weather modeling is a few hundred meters. So this was used to develop, as a forecast, several days into the future, in real time, wind and weather predictions for this area here under red flag warning conditions. And as I mentioned, this was done as a Monte Carlo simulation, and out of the thousands of simulations that were conducted, I just sort of picked 3 at random to look at the fire shapes that develop and the fire sizes that can occur. So the nice thing, or one of the nice things about this approach, is that by necessity, all the data that go into the model, as well as all the data that come out of the model, are geo-rectified. So you can take them and visualize them in whatever way is appropriate. If you have high-resolution ortho photos, you can overlay the fire perimeters on that. You can even import it into Google Earth, which is what I've done here. So for the first fire, which begins on the east side of French Meadows Reservoir, you can kind of see this red blob here. This is the fire perimeter after an hour. And we see after 2 hours, it's grown in size. This distance here is about 2.5 kilometers. And by 5 hours, it's reached about 80 hectares, and we see this classical. Some of the things that are ongoing now include development of spotting submodels. This is a dominant way that fires spread under hot, dry, and windy conditions. So I have most of the submodels for ember generation, wafting, trajectories as the embers fly through the air, and then ignition, which has to do with the properties of the embers as well as the receptive fuel bed upon landing. Most of these are worked out and being tested. There's several different ways of modeling campfire initiation and propagation. These have been implemented and are again being tested. Validation is, of course, a very important part of any type of model development. That's underway. And then as far as sort of capabilities, there's a simple Monte Carlo simulation approach. In fact, we're going to hear more about Monte Carlo simulation at the end of this session. Or maybe not, I think that paper was canceled. But there's also possibility of using this Monte Carlo approach to do, say, an automated sensitivity analysis. That's really one of the motivations. And farther on down the road is using, say, an evolutionary algorithm to do automated model calibration. And then even farther on down the road is a relatively new area in fire research, which is using data assimilation to steer the fire as it develops and grows in space. And then finally, there's, as this is an open source project, there's the ongoing dissemination through a separate repository. So thank you for your attention. Are there any questions?
Thank you for your presentation. Now it is open for discussion. Yes. Please.
One suggestion. We are beginning now a collaboration with the civil protection here in Cantabria.
Great.
They have a lot of many small tests controlled in wildland areas. I suggest you can use this collaboration using the data for validation and similar. But the question is, I have the similar question for Marcos. The industry wants to know the computational cost, the computational time for transferring the knowledge for the products. And here, which is the computational cost compared with the former approach or the former model?
For this, seconds to hours, meaning seconds of computational time is hours of real time. And this type of approach is what's called embarrassingly parallel, meaning it's trivial to run, if you have like FM does, a 1024 CPU cluster, it's trivial to run 1024 of these simultaneously because you don't have to transfer a lot of information over the network. So it's very easy to parallelize. So, core per core is, I don't remember exactly, but it's on the order of a few seconds for a few hours of simulation time. But it can be run in parallel. Right.
This is the approach, the real time.
Right.
Great, nice talk. My question is more about your ongoing work regarding firebrands, firebrand generation and transport. Are you going to be approaching that as kind of like stochastic in terms of mass, size, temperature, and so on?
Yes.
Okay.
And that's really one of the motivations for developing this with an eye toward Monte Carlo and parallelization is that by its very nature, spot fire formation is an inherently stochastic process. And currently the approach with Farsight is usually to run 1 or 2 or 3 simulations where you have to input the firebrand emission probability. And I think really the better approach is to run literally thousands or potentially hundreds of thousands of simulations and then compare it to an actual fire perimeter to get an idea of how to bring the model into better alignment with the observed fire behavior as far as spot fire formation. So yeah, everything's stochastic using PDFs, basically.
How does this differ from WFDS? Do they also use a Wolfram model?
No, WFDS, well, there is a level set method that's implemented in WFDS,
Right.
and I believe it uses a physics-based approach. In other words, the rate of fire propagation on the fire line depends on radiation heat transfer. So this is the difference between this and, say, WRF fire or WFDS. Those are both physics-based models where the simulation time is on the order of 1 to 1. You might need an hour of simulation time to simulate an hour of real fire behavior, whereas this is seconds of simulation time to simulate hours of real time. So it's really aimed at a different purpose, which is prediction into the future or rapid assessment over large geographical areas we've used this approach for mapping wildland fire hazard across California, for example.
Great work, I think. What I would like to ask is something more practical. How can we include suppression in this model?
The way that suppression is handled in Farsight is basically by taking individual raster cells or grid points and masking them as non-burnable. So as the hand crews are in and dozer lines are being built, they dig it down to bare mineral soil, and that's basically how fires are contained and suppressed. And so there can be a representation of that in models such as this or in Farsight, where you basically change the fuel complex from a burnable type to a non-burnable type. Something like aerial attack, where there's retardant being dropped, is more difficult to account for in this type of a model. The hand lines are still the predominant way that fires are suppressed.
Do you know the critical times of safety protection? There are critical.
Yes. So many feet per hour of fire line are built. So yeah, that's been studied and can be added in. It's a good point. Pardon? Backfire. No, there's no fluid mechanics in this other than the wind and weather conditions that come from whatever source, whether it's numerical weather prediction or something. So there's no interaction between the burning fire and the ambient conditions, which is, I think, what you would need to be able to simulate a backfire where the fire is drawn into the fire line. So something like WFDS or even potentially warp fire would be appropriate for that. But this model is for wind-driven surface fires where there's limited interaction between the fire plume and the ambient wind and weather conditions.
Well, thank you
Thank
very
you.
much for the presentation.